Okay, discharging a capacitor. So, I mean, some capacitor is charged and somehow there is an initial charge in here. So let's say it like this. It has an initial charge in here. And then somehow somebody actually connected the two plates of the capacitor with a wire. And so therefore the capacitor started to discharge. But of course, every wire has a resistance. So what we did is actually, in that case, we connected the capacitor in series with a resistor, and then we just connected the two plates like that, right? But we usually state this problem like this. So let me write it down like that. Okay, so the switch S is closed at time t equals 0, right? Let's say it like this. So find the currents and charge at, find the current and charge at time t. So that's the question basically, but it's an incomplete question. So when I ask you this kind of a question in homeworks, you should say we cannot solve it because you didn't define what the current is. So if I didn't give you any reference frame, then you have to provide the answer together with the reference frame, right? In any case, so again, let's say that the charge is the charge on that plate. So I'm going to draw the picture again, right? But this time I'm going to write down the variables. Right, so that's the circuit now. It's an RC circuit, so there is no EMF device in here. And our variables are, so I'm going to call the charge on this plate as Q. And I know that this charge is going to be emptied along that direction, so therefore it's going to produce a current along this direction with a positive value. So therefore, I call the value of the current, I call the current along this direction as I, all right? So these two are important. So I have to specify which plate, because the other plate has the negative charge. And I have to, for currents, I have to specify a direction. So that it's the direction along that current, okay? And then we have these. So there are these initial conditions. Well, it's just one initial condition. So the charge at time t equals 0, if you consider charge as a function of time, it's given as this value in here. It's the initial value of the charge, right? So somehow my solution should also satisfy this property, okay? So I'm going to do the same thing as I have done before. I'm going to first obtain a relationship between the charge and the current, yes. And then I'm going to write down the circuit equation. And well, basically I just connect these two. So the first thing is, let's say it like this. So this is the relation between, relation between the current and the charge. How do we find this? The picture is very simple, right? I'm going to show it like this. Again, it's the same picture, but I'm isolating this part, right? So this current I is flowing towards the negative plate, or if you want, it is flowing away from the positive plate, okay? And so therefore, the current is equal to minus dq over dt, all right? You can think of it like this. You can think of it in many different ways. One way is like that. So if this current is positive, that current is positive, so this current is positive, which means that the charge on this plate is decreasing if it is positive. So when dq over dt is negative, then the current is positive, so there has to be an extra minus sign in here. You can think of it like this, right? I mean, you just think about a scenario where the current is positive and the charge is positive, and then try to understand by using the physics which equation actually gives you the correct relationship, right? That's one way. The other way, what's the other way? The other way is this. I have said this. For example, this current is filling up this plate, and that plate has charge minus Q. So therefore, I say that the current is equal to the rate of change of the charge on that plate, which is minus Q, which gives me the same equation. Or I can think of it like this. So I know that if the current in the upward direction is positive, then the current in the downward direction is minus I. Sorry about this. If the current is in the upward direction is I, then the current in the downward direction is minus I. Right? That's the correct thing. So in that case, this minus I current is filling up the charge on that plate. So that means the current, which is minus I, is equal to the rate of change of the charge on that plate, right? So therefore, I mean, whatever. I mean, there are many different ways that you can think about this. But in this special case, the current is equal to minus dq over dt. All right, that's basically one of the things that you have to be careful with. Second thing is this, what's the circuit equation? So I think I'm going to shift this to the side. Circuit equation. So in that case, I'm going to do it like this, because I don't actually think easily. I mean, it's not, there's no magic formula in here. So if you can easily confused, so as a result, for these kind of cases, just think in the way that I'm thinking. So just label some points in here. So let me call these as A, B, and D. So I know that the VB is equal to VD. So therefore, because of that, this potential difference VAB is the same thing as VAD, right? That's basically what we would be actually using. But in any case, VAB is potential difference across the plates of the capacitor. So I know what the formula for this one is. So I know that if Q is positive, then A is at a higher potential. So therefore, this VAB is equal to Q divided by C. And for the resistor, I know that there is a current flowing along this direction. So therefore, if current is positive, A is at a higher potential than D. So if I write this formula, VAD, in that case, this is going to be equal to I times R. So therefore, the circuit equation is this. I'm sorry about this. I shouldn't say circuit equation. So this is basically the loop rule. Well, it's a circuit equation, but this is it is the loop rule that we are applying, right? The fact that the potential is a well-defined function. So that's basically Q over C is equal to I times R. Okay. Again, two key relationships. One is the relationship between the current and the charge variables. And the other one is the physical one. Yeah, it's the loop rule thing, right? I mean, this is the equation that gives us how the current changes with time. So probably calling it physical is not a good idea. So everything is physical, obviously. Everything describes the physics. But that's the one that gives us the how the current will change with time, right? Let's say it like this. Okay. So I don't know if you have any questions. So that's basically the part that we need to get over with. Now, for the other part, let's see. For the other part, what's the other part? Yeah, I need to solve this, right? But of course, it is these two equations together. So I need to make this as a differential equation. So that's dq over dt times r. So this is a differential equation that is more manageable than the previous one, because I don't have any constant terms that appear on the right-hand side. That's good. So therefore, from here, I can immediately write that the charge is equal to some constant times multiplied with e to the minus, well, this is the one that appears inside the argument of the exponential. Let's say for some constant a, right? But what we do is, we just, I mean, there's some kind of in the general solution, there's an arbitrary constant that appears. We need to compute that constant by using initial conditions. So find a by using initial conditions. Depending on the initial condition, it's going to have a different value. So what's the initial condition? So the value of the charge at time t equals 0 is given. So that's the one of the variables in the question. So I know that this is q0 is equal to a times e to the minus 0 divided by something, whatever. So that's basically 1. So that constant has to be equal to q0. So therefore, from here, we find q to be equal to q0 times e to the minus t over rc. Yes. And you find the current to be equal to, it's basically the negative of the time derivative of this. Negative sign is important again, so that's therefore q0 divided by rc times e to the minus t over rc. All right, let me quickly draw the time versus quantity versus time graphs. So Q basically decreases like that, and the current also decreases like this. I'm also going to draw the circuit as well. Both of them decrease. Let's see, this is the circuit. Let me also show these with the yellow colors again. So that's the current, and that's the charge. Right? Sorry about this. This is not the EMF. That's the capacitance value, right? Capacitance value. So initially, Q0 was the charge on the plate, on the upper plate. When I connect these two positive and the negative plates with a wire, the charge does not immediately disappear. It just takes some time, right? So how much does it take? Well, I need to use the time constant value in here. So that's the time constant value. So let's say it like this. Within, let's say, 3 to 5 time constants, you can safely say that the capacitor becomes completely empty. Okay, but again, it takes the time constant amount. So basically, I mean, in the charging and the discharging process, the time constant of the circuit is the relevant time constant that we should be discussing in here. This is basically, I mean, for more complicated circuits, I will be talking about these. Is basically the capacitance multiplied with the resistor, which is connected in series with it. So basically, you remove all of the EMF devices and try to simplify the circuit like that. In any case, I'm just going to say something more about more complicated time constants. Okay. I don't know if you have any questions in here, and I don't know yeah, that's the, sorry about this. So the discussion of the values at t equals 0 and t equals infinity. So this is something that I can similarly discuss before. just as I have discussed before, right? So for this circuit, so let's say it like this. Let's say values of I and Q at, let's say, t equals 0 at the initial time. So Q is equal to Q0, that's given. What's the current? Well, initially the current is actually, before switch is closed, the current was equal to 0. So let me kind of show it like this. I think I'm going to use a strange color like that. So the current actually after the switch is closed decreases like that, but before the switch is closed, it was equal to 0. So somehow the current becomes switch from a 0 value to a non-zero value. So a discontinuous change is usually not physical. So we know that the current is going to change continuously, but it has nothing to do with the circuit. So we are going to discuss this later. So we are going to say that there's some kind of an inductance in the circuit, and that's the one that somehow prevents the sudden changes in the value of the current. So right now, for this simplified picture, we can say that the current can change suddenly. No problem with this. But the charge on the capacitor, it doesn't change suddenly. So this has to change continuously because of the presence of the resistor in there. The capacitor cannot immediately discharge. It just discharges with some certain time constant, okay? But somehow the current can change discontinuously, and so that's okay. So in this situation though, I mean, we know that the initial charge is given, and so therefore there has to be an initial current. I cannot use a continuity argument to find what the current is, right? That's the problem in here. But now I can use this potential difference picture. So I know that these 2 points have a potential difference. So I think I call this as A and this as B, and this is D. So I know that there is a potential difference in there. So to find the current, I need to find the potential difference across the resistor. So basically the potential drop on the capacitor, which is basically the potential difference VAB, is the same thing as the potential difference on the resistor, which is basically the potential difference between the points A and D, right? So I know that at the initial moment, basically it is this, right? I know that at the initial moment, the potential difference across the place of the capacitor is Q0 divided by C. And so therefore, this has to be equal to the potential difference on the resistor, which is given by the Ohm's law. And then from here, we find the value of the current at time t equals 0. So that's the current at t equals 0. Okay. So the charge is given. So it's not hard to find this. We can then compute the current because somehow by using this value of the charge, I can also find the potential drop on the resistor, right? This is how we can compute, no problem. What about the infinities? So I just go down, right? Let's say what are I and Q at t equals infinity? So this is our circuit. All right, and the capacitor. So obviously nothing is changing. So basically Q is a constant now, and the current is a constant now. So that's the thing that we can say. So at time t equals infinity, all of the quantities becomes constant. When the charge is constant, so the current has to be equal to, it's the rate of change of the charge. It doesn't matter what the sign in here is, the current is equal to 0. Okay. And if the current is equal to 0, so therefore the potential drop on the resistor is equal to 0, which implies that the potential drop on the capacitor is equal to 0, which implies that the charge on the capacitor is equal to 0. Right? That's also kind of obvious too. You can also intuitively expect that the charge to be equal to 0. Okay. So in any case, you can do also these shorthand, this magic circuits like, I think, replacing the capacitor with a wire at t equals infinite. But these kind of things are always more complicated than it seems. So when you are changing the circuits, there are some certain things that you have to be careful with. So as a result, I mean, if you can do this analysis, I suggest that you do it like this. So that's the correct way of doing the analysis. Okay. All right, so there's another thing in here, right? More complicated RC circuits. I'll start with this one. So I'll start with the circuits where there's only one capacitor. But let's just say it like this. So suppose that I have like 2 resistors now. So this is kind of immediately obvious what it is. So yeah, let's say it like this. Okay, so a capacitor is connected in, I don't know, in many different things like that. So in these kind of situations, what is important is perhaps the time constant in here. So the time constant in that case is equal to the capacitance multiplied with the equivalent capacitance in which this capacitor is connected in series with. All right. So let me say it like this. So somehow, if you just remove everything in here, I mean, just simplify all of these resistances to a single equivalent resistance, right? That's basically what the capacitor sees as the resistance between its plates. And so therefore, it's the one that you need to write this thing down in here. So I think in that case, this is like R1 plus R2, R3 divided by R2 plus R3. But in any case, so without doing too complicated questions or writing down the circuits and things like that, I can immediately write down what the time constant is. Okay. So as a result, I mean, this is just an example. I'm not going to solve any problems like that. But to find the time constant at least, you can do this. Let's consider a little bit more complicated RC circuit. Where we now have an EMF in here. Right? So I'm going to do it like that. And perhaps in here too, there can be some switch in here or whatever. Forget about the switch. I mean, usually switch is used to actually establish some initial conditions and initial time. So as a result, this existence is completely irrelevant. So this is just like the previous question, except that now there's an EMF device in here, right? So what's important in here, in this example, is that the value of the existence of the EMF device actually doesn't change the time constant. So let's say it like this. The time constant does not depend on, depend on the presence of an EMF device or does its EMF value. So the time constant has nothing to do with the EMF. So the EMF somehow determines the maximum amount of charge that will be filled on the place of the capacitor when it is completely filled, all right? And so as a result, it's basically independent. So as a result, in that case, the time constant is basically given by the same expression, right? So that's basically R1 plus R2, R3 divided by R2 plus R3, right? So that's the same again, same as the previous circuit, right? But of course, the the time dependence of the currents and whatever the value of the currents at infinity and things like that. These are going to be different now because this is like a charging circuit now. Okay, so in this case, so that's about the time constant. The second one is this, what happens in here. I mean, at time t equals 0, perhaps you can actually find the currents and things like that. But what happens at time t equals infinity? Let me describe it. Sorry about this. I'm just going to draw the same picture again, but with a bigger one. All right, let's say it like this. So there's an EMF in here, and there are these resistors in here. Okay, so at t equals infinity, so that means the capacitor is full. At t equals infinity, this is completely filled. So therefore, the charge on it will not be changing anymore, and which means that the current on that branch or along this, doesn't matter, the current on that branch is equal to 0. Okay? So this is something that you can immediately say. And so as a result, if there's a current in here, let's say I2, that current is going to be the same as this current in here. So let's say I2 is equal to I3. Okay, so so therefore there is a current that must be flowing in here, which then implies this. So I'm just going to use some other color in here. So let me call that point as A and that point as B. I can also say this. Probably this is not the one that I should be talking about right now. But in any case, based on this, I can therefore say this. I don't have space left, so let me make this smaller so I can do these kind of things. So therefore, the potential drop on the capacitor is equal to the potential drop on between A and B, because there is no potential drop on this resistor because there is no current flowing in here. So whatever the potential drop on this one is, that's equal to the potential drop on this branch of the circuit in here, which is essentially the potential drop on the resistor R2. Okay, so if I can find what that current is, I can basically find what that potential drop is. And from here, I can then compute the amount of the charge that must be on the capacitor, right? So let me just say etc. in here because I don't want to solve this problem. But I think in the homeworks, I'm going to ask you questions about these kind of things, all right? So at t equals infinity or at t equals 0, by using some kind of physical reasonings, you will be able to compute every circuit variable. So basically, at t equals infinities, there will be no currents passing on the capacitors. And by using this, you can essentially solve the rest of the circuit. Right? What I'm trying to say in here is that in these kind of circuits, it's possible that some currents can be flowing within the circuit. They will continue to flow, but you can find the values of these currents by using these kind of physical reasonings, right? Let me state it like that. Sorry about that. So let me, yeah, I have some difficulty in arranging the magnitude. Okay, another thing in here, in these kind of circuits, let's say it like this. I'm just going to do it like that. Again, let's talk about the circuit. And suppose there's a switch in here. Let's say S is closed at t equals 0. Let's say that this kind of an information is given. And whatever, I don't want to actually use the labels in here, but let's just talk about, for example, the current in this branch. So the question is, find the time dependence of the current I2. I mean, write I2 as a function of time. Okay, so the idea in here is this, right? I mean, you can basically write down the differential equation for I2 and solve it. That's a possibility. But there's a nice trick in here, right? This current I2 or any other current or the charge variable on the circuit always has a certain time dependence that we have seen, right? I2 has a time dependence of the form where I2 is equal to some constant plus some other constant times e to the minus t divided by tau. Tau is the time constant of the circuit. So we know how to find this, right? This is this is C times some equivalent resistance. Here, A and B are some constants that you need to find. So where A and B are some constants. So at the end, when you compute the current I2, you are going to find this expression. So as a result, you don't have to write down a differential equation and try to solve it and things like that. You can directly start from this, right? That's a possibility. And in the, I think, the chapter 26 homeworks, I'm going to ask questions like this, right? This variable has this kind of a time dependence where there are these two unknown constants in here. Find what these constants are. And finding the constants is actually quite simple because you can analyze the circuit at time t equals 0 and at time t equals infinity. So I know that. So let me, again, make this a little bit smaller. So I know that, let's say, at time t equals 0, this current expression is going to give me A plus B. So this is the value of the current that at time t equals 0 is. But I can compute this physically, right? For example, if that's the problem, and if the switch is closed at time t equals 0, so before that, the capacitor must be empty, so therefore there should be no current in here, right? Is that so? I'm not sure about this. So in any case, so, right, find this independently. Sorry, there should be a non-zero value for this. So at time t equals 0, you are going to replace this capacitor with a wire and then solve the circuit like that. In any case, at time t equals infinity, this expression gives me just A. And you can also compute the current at t equals infinity, right? And so as a result, by just computing by using the values of the current at time t equals 0 and time t equals infinity, you can then find these two constants, A and B. And so therefore, you can then find what A and B are, right? So therefore, find A and B, and then after that, you're going to find the value of the current. Okay. So in any case, I'm not going to ask these kind of questions only for some simple circuits. You can think of it as some kind of an exercise, right? Even for simple circuits, you can do that. Okay. So the next question is this. How about the RC circuits like that? Where, sorry about this. We have two capacitors. So let's say C1, R1. Let me show it like that. This is C2, R2. And then there's R3 in here. And perhaps an EMF device placed in here or whatever. Okay. So the problem with these circuits is that let's say it like this. This circuit has two time constants. Right? There are actually two numbers that describe the behavior of this circuit. And so as a result, any kind of a quantity can be written as a sum of three terms, basically. I'm just going to tell you this to show you that these kind of circuits are actually quite complicated. But I'm not going to do any calculations with this, and probably you're not going to see any problems in physics that has these kind of things. But just think of it, I mean, just keep this in mind that, I mean, these kind of circuits are usually a little bit more complicated. They in general have two time constants. And so as a result, we never go into these kind of things. But in the past, I have asked these kind of questions like, for example, an EMF is connected to some kind of a resistor in here with resistance R1. And then like there are three capacitors, but all of them are identical with each other. And then the question is to actually find time constant of that circuit. So this kind of a circuit too has, in that case, it has three time constants. But if it's a definite problem, like the charging of this one, like you close the switch at time t equals 0, and then initially all of them were empty, and then you just look at this, I don't know, the circuit. So in that case, you know that by symmetry arguments, you can easily see that the current somehow entering in each of these branches is equal to I over 3. And so as a result, you can easily write down the circuit equation and things like that. So as a result, you can solve this kind of a circuit. Luckily for you, in none of the online homeworks, I have a question like that. I don't have it. But if you look at the past homeworks, you're going to see questions like that, right? I mean, it's something that you can easily analyze and solve. In reality, though, the actual circuit for an arbitrary connections is actually much more complicated than this. Okay. I think there is only one thing left in here. It's basically the energy. Energy in the case of charging a capacitor, in the charging and discharging circuits. What happens to the energy? So I haven't decided on this thing yet, but probably tomorrow, for example, I can talk about this in the first hour. But in the second hour, definitely I'm going to pass to the new chapter, because we have to go, we have to see some parts of it. In any case, that's it for today. So let me stop the recording.